So I'm Javeria Kapoor and I'd be presenting the problem jumping beans along with Mehreen Shambir. So the problem statement was a simple toy called a jumping bean can be constructed by putting a metal ball inside of a pill capsule placed on an inclined surface at a certain inclination. The jumping bean will tumble down in a rather surprising way, seemingly standing upright, flipping end to end instead of rolling. Investigate its motion and find the dimensions of the fastest and slowest beans for a given inclination. So our interpretation of the problem statement was as follows. Why the capsule topples instead of rolling, explain the dynamics of the tumbling motion, and for a given inclination, what are the dimensions for the fastest and slowest beans as observed experimentally. So moving on to the theoretical model, here you can see our reference formulas, some reference formulas. First, you can see the Rayleigh dissipation equation, where G is the dissipation function, such that the dissipation force F equals to the negative of the gradient with respect to the velocity of the object of G. And then you can see our modified Lagrangians and modified energies, L prime and E prime. And on the bottom of the screen, you can see the Euler-Lagrange equation. So now discussing why the capsule topples instead of rolling. The capsule can roll downward with the ball inside rolling downward as well. A slight shift of the ball from the center of the capsule will cause the tilted end of the capsule to come forward, and this would yield a topple, continuing it again and again. The tumbling of the ball down an incline can be divided into two subsystems, system 1 and system 2. So system 1 is when the ball rolls from one end of the static capsule to the other end with a velocity theta 1 dot. As soon as the ball collides with the capsule, assuming perfectly elastic collision and taking into account the energy loss due to the presence of friction between the ball and the capsule, there is seen a transition from system 1 to 2. You can here see the equations, the Rayleigh dissipation function equation, which we catered for our equation of motion, and then we got the equation of motion as theta 1 double dot as seen on screen. The total energy after subtracting the dissipated energy is E1 prime, and the parameters are listed below. So moving on to system 2. System 2 is the ball capsule system now moves with a velocity theta 2 dot, and the capsule topples with the center of toppling coincident with the center of rolling of the ball. As soon as the capsule falls down, assuming that the capsule ball system collision with the surface of incline is significantly inelastic, the capsule rests static and system 1 is achieved. So you can here see the equation for G2, which we kept in mind while writing our equation of motion for theta 2 double dot, and P and Q are as follows. Now moving on to the numerical solutions. The obtained equations of motions of theta 1 double dot and theta 2 double dot are solved numerically using Euler method to get the time taken to topple down a certain incline. So in our while solving numerically using the Euler method, we initialize theta 2 dot with the following assumption. The collision of the ball with the lower end of the capsule is assumed to be totally elastic. This assumption restricts theta 2 dot to be such that at theta 2 dot equals 0, E2 equals the modified energy E1 prime, and we get theta 2 dot square as follows. Initialization of theta 1 dot was with the condition that theta 1 dot of the current system 1 equals theta 1 dot of the previous system 1. And applying this assumption, we get a simulated T versus alpha plot as an asymptotic curve to the experimental data, as you can see in the graph here. The purple line, it is the simulated data. The purple bold line, which is acting as an asymptote to the experimental fine lines above, is by using this certain assumption. The orange line is when we when we also considered the effects of friction, but it was still not fitting our experimental data. So we introduced a fudge factor. As angle alpha increases, we see that the experimental curve converges to the theoretical curve, and we introduced the fudge factor f alpha equal 1 over sine alpha in the dissipation equation. Now the simulation fits with the experimental results as seen by the bold blue line. So moving forward, you can see the simulation results. You can, in the above diagram, there are the average times for 5 different capsules. On the x-axis there is the angle of inclination, on y-axis there is time, and you can see that the above graph the experimental data and the below graph the simulated data, they show the same trend. Moving on to standardized experiments.
Okay, hello everyone, and my name is Mehreen, and I'll be dealing with the standardized experiments. Okay, so if you can see in the slide over here, this is the basic apparatus that we use to conduct our experiments. The apparatus was that we used aluminum foil to custom make our capsules, and then we used ball bearings of different radii to act as the ball inside the capsule, and we used a wooden plank as a slope, and we mounted it on 2 slides. The parameters varied with as follows. The diameter was changed from 4.8 to 9.5 millimeter, length was from 17 millimeter to 32.5, and inclination was from 5 degree to 31 degree, because after that the capsules, they tumble too fast to give any proper result. If you go to now in this slide, you can see that we have analyzed the length and diameter of the capsules with the inclination and the time. So if in the first graph, you can see that for a constant length, the diameter is inversely proportional to time. So if you change the diameter, the plot slightly shifts, and if you go to, and if you see the right plot for a constant diameter, the length is directly proportional to time. So this sort of so this sort of suggests that there is a linear relation between them. But then when we however, if we combine these results, we get such a graph where you can see that there is no general trend for all these plots. If you look at the one instance of time, for example, you can see that there are 3 different sets of dimensions of diameter and length for which you get the same result for time. So the variable okay, so in the so here you can see that we try to find the extreme times at different inclinations. As you can clearly see that no one series one for all the inclinations, and different inclinations you have a different fastest capsule and a different slowest capsule. So these were the experiments, and these were the different sets of experiments that we did with the different series that we mentioned previously. And now is the numerical optimization. So here you can see that so one way to numerically optimize this problem is that you, while borrowing the theoretical model, you can try to optimize each parameter separately while keeping the others constant. So for example, in the first graph, you see that we have tried to change the length, and then we plotted it against the total time taken by the capsule to come down the plank, and you see this sort of trend while we kept the other parameters constant. And then you can see this is the sort of trend that we got for for changing the radius. So so the way to numerically optimize this is that we can fix certain parameters in the simulation code and run it for a certain varying parameter, giving us a general trend for that parameter. So now the ND optimization, the numerical optimization, is that we can follow the same approach as mentioned before and optimize each variable separately. We can combine the results to give us a complete optimization involving all parameters in n dimensions. This way we can get the dimensions corresponding to the extreme values. Now some improvements which can be made to the theoretical model is that we can use a better fudge factor, which can be thought of by analyzing the fraction of energy which is transferred in every fall of the capsule, using high-speed laser cameras to find the total velocity and then the total energy which is lost. And for the experimental model, the consistency of aluminum could be improved, as the surface structure of aluminum capsule, it deformed over the course of the experiments due to repeated trials. So that's it for jumping beans. Thank you.
My name is Aaron Palonica. I'm from the Russian team, and I'm happy to represent your proposition of the problem number 14, jumping bean. So let's firstly talk about what was done with the report. for the first frame, we were given the modified Lagrangian equation, which what he used to simulate his spin motion in theory. But unfortunately, it wasn't explained enough. So I think it would be good to talk about it a little bit more about these equations, how the body gets them, and its use. Excuse me. Next, we'll talk about we're given the equation for torque equations, and it allows where we saw the friction force, and what I used the case for only slipping force. But I think it's not good to say it, that we have slipping motion without any trying to prove it. So we'll talk about it later in discussion. Also, it won't mention that we have some dissipation in energy in the system because of the friction, but I think that not only friction can be used of dissipation energy, and there's also one point which we'll talk about later in discussion. Also reported talk was possible to make a theoretical prediction for time needed for ball to go down as function of inclination angle. Unfortunately, it was a little bit not clear because we saw some oscillations there, and the reason for this oscillation wasn't explained. Also, in experimental part, what we write the capsule's length, capsule's diameter, and length inclination angle. But I'd strongly recommend reporter also to check if change densities of capsules and have experiments with ball that he put inside the capsules. So if we talk about the strong and points to report and points which can improve, the strong reporter tried to find the dimensions of the fastest spin in theory, but unfortunately it wasn't clearly checked compared with experiment. We had a really good agreement for plots as time of inclination change with how time of needed for me to go down change with inclination angle. So that's a really good point, in my opinion. And also some points are that reporter change the capsule length, capsule diameter, and also the inclination angle. But of course, there are some points to improve, and the three main points to improve is to add the range of applicability of reporter theory, for example, of slipping model. Also, in experimental part should improve. For example, as I got from the reporter released his spins by hands, but in this case, we don't have enough control on initial parameters, such as initial velocity of the beam, and also 3D motion, which is really important in this problem, couldn't be controlled in this case. So it's a really important thing to improve in your work. Also, unfortunately, it wasn't clear for me show dimensions of the slowest beam with comparison to experiment. And if you talk about the parameters which reporter should vary, there are 3D motion of 3D motion of the capsule and ray ball we should put inside the capsule. And finally, if we talk about the task flow of the problem, we will say that this problem was solved only partially because, in my opinion, standing up was not clearly investigated. Also, we have some questions about model of beam motion. So there was a clearly found dimension of fastest beam, but in my opinion, it was more like missed dimension of slowest beam. And also, in my opinion, main role of inclination angle wasn't explained. So now I'm ready to go to discussion, and I asked the reporter to go to the online board I've sent in the chat. It's IDO board, and I think it will be better for us to describe and draw some picture. It will be better for us. So can you please do it?
Okay, so you mentioned that we did not include the slipping model in our theoretical model.
No, I said that you include slipping model, and I want to. So okay, let's firstly describe in this case applicability of slipping model, because don't you think that not always this model is correct? For example, what happens if the angle of inclination is really small, about 2 or 3 degrees? Will we have, in this case, slipping motion?
We actually experimentally first determined that on which angles this toppling motion occurs, and we only applied our theory to those certain inclinations. And second, we did not, we agree that our theoretical model, it only includes the tumbling motion and it does not incorporate the slipping effects. So you mentioned that we did not talk on the human factor. The error bars that we have calculated, they actually include the human factor, and we basically did video analysis of all our we recorded videos, and we later on performed video analysis of the capsule tumbling down the incline. And while performing video analysis, since our camera was of 30 fps, so that way our experimental error, the human factor, comes out to be the error comes out to be of 0.03 per reading. And
thank you. I got it. I think let's better go to the discussion. Sorry for interrupting. Let's go to the discussion. And first question I'm going to talk with you about is the role of this inclination angle. So let's talk about firstly on qualitative level. What happens if it increases angle alpha? How do you see?
All right, we let us share our screen.
I'm sharing the screen, so I think all can. So if you write something, all will see it.
Okay, so what happens when you?
Yeah, on qualitative level, in a few words. So like time increase or decrease, and why? Just without some complicated equations.
If you can see on the x-axis, we have the angle of inclination. So it goes from
okay. Let's talk about this. So in this case, let's talk about this plot a little bit more. Why do we can see that on green line that there are some oscillations on time? Can you name the physical reason of it? So what is the reason? Why do they select?
Basically, the surface of the board, it is not overall smooth. It has different values of friction over the board at different locations, and in addition to that, the capsule, it tumbles, and in between tumbling, it sometimes attains a rolling motion too. So what you can see here in this graph is that you can see 3 trials of the same capsule.
Sorry for interrupting.
5 lines you've made.
Sorry for interrupting, but can you please explain the physical reason for this green oscillation of green theoretical curve? It wasn't clear from your explanation.
There are microscopic friction effects in the board with the.
And do you think that this microscopic friction effect can be the reason for time oscillation?
Yes.
So I disagree with it because, in my opinion, microscopic friction can affect, but we can clearly see from this plot that it changed time of motion for about 1 second, on about 30%, just for microscopic effects in such a big scale problem. So I disagree that this can really be important in this case.
No, but there are other reasons towards this too, that sometimes the path changes. Since we have not we have not included the 3D path.
Sorry for interrupting you, reporter. So can you hear me again? So if you say that the reason for this oscillation is a microscopic effect, maybe you can prove it somehow with your experiment with changing this microscopic friction change, or you only think that it's microscopic because of microscopic friction.
But I did not interpret your question.
My question was that you say that we have such deviation in this plot because of microscopic friction. And I ask if you can prove that this is really by microscopic. For example, if it is microscopic friction, maybe you change such scale, or you only think that such installation of the plot is caused because of microscopic effect.
Well, since there was this effect of friction, what we have done is we have taken 3 trials per capsule, and here you can see 3 different trials of a single capsule. Capsule was labeled capsule number 5, and if we average out the readings for capsule number 5, you can see that here it is represented by a better and a smooth curve, and these are the average values curves. These are for 5 different capsules: capsule 1, capsule 2, capsule 3.
Thank you. I got it. Now it's clear for me. That's clear for me. Thank you. Let's now please go to the online board. I'm going to describe with you a little bit qualitative physics, just basic for this problem. Can you please name the reason why does this capsule rotate? So what happens if we put just beam on a inclined surface without ball inside, just capsule, plastic capsule with small inclination angle? Will it go down or not?
If the angle is high, it will still.
No, with small angles. What will happen?
But small angles, it depends on the material of the capsule, too, the friction between the capsule and the surface.
And if the friction is high enough, what will happen?
And we also tried these. We also tried this experiment. We actually tried these experiments.
No, on qualitative. Can you please say it in qualitative level? What happens with without complicated expressions, just with easy way of physics, like for example, it won't move because friction force will be high enough, or it will move because of something like it. Can you please?
Why it basically topples, or the second condition you have put, that when a ball is not in the capsule.
And what happens if we put ball inside the capsule? So if, as regards that capsule without ball don't always move, if you put heavy enough ball inside the capsule, will it stop motion or not? How do you think?
So basically, the capsule, it seemingly stands upright, and this actually there is an element of the friction between the capsule and the ball, and the capsule and the surface involved in all of this motion.
Thank you. Now we have a question from the team. Sorry for interrupting you.
Hello. So my question is, am I right that you solved Lagrange equations numerically?
Yes, we solved them numerically.
Which method did you use?
We used the Euler method, and
why did you use?
Here is the algorithm for our.
Okay, I get it, but why did you choose the Euler method? Because the error during the calculation isn't constant, and this error accumulates during the whole calculation. So why didn't you use, for example, a Runge-Kutta
why didn't we use some other technique? Well, we used the Euler method. We used the Euler method to solve our equations because we wanted to solve for time t theoretically, and we could not theoretically extract the equation of time t from our equations of motion theta 1 double dot and theta 2 double dot. They were too complex to explicitly extract the time t from them. So we used the Euler method to find the time t, and we were trying to see if our theory fits the experiment.
Okay,
so
okay,
that's why.
thank you.
And then we saw that our theory does fit the experiment, and then we also showed the results.
Thank you. I got your answer, but personally, I think that it's better to use Runge-Kutta method, for example. My next question is, please, can you open slide with your comparison between theory and experiment? So yes, this one. So previous one. You should. Yes. So on the left, we can see a clear difference between the numerical simulation after solving your equations and the experimental one. So why there is?
Well, our theory, while developing a theory, you are not, you try to, but you cannot consider all of the experimental factors or the real life factors. So we took some assumptions while developing our theory and while solving numerically for it, and we also discussed those assumptions. And after taking all of those assumptions, we saw that our theory with it um, fits the general trend, and you can see that it is an asymptote to our experimental data. And then we introduced a fudge factor to it, and the fudge factor, it can also be further improved, because the reason for introducing the fudge factor, as mentioned in the improvements section, is that the fraction of energy transferred in every fall of the capsule, it is a bit different, and it can be analyzed and recorded by analyzing the motion using high-speed cameras. And we did not have high-speed cameras, so we could not include this in our model.
I'm not sure I understand why the limit speeds are not 0 and infinity. I mean, if you choose a reasonable angle, say 15 degrees, it can take forever for the capsule to stand upright if you get the length just right. And if you make a short capsule that's almost like a sphere, then it will barely slow down the ball inside, and the speed, in my naive opinion, might go to infinity. So can you comment on this?
So maybe I'll start. Is it okay?
Okay, so yes, you're right. Ideally, it would be that way. But while performing our experimental data, while performing our experiments, we chose that certain inclination. We have given that certain range of inclination here, for which we saw topples. For the inclinations in which the topple never occurred, that is, it just slipped down, the capsule ball system slipped down the incline, that is less than 5 degrees, and for angles greater than 31 degrees, the capsule, it no yeah I accidentally said it upside down. So for the 5-degree inclination, less than 5 degree, it did not move, and for angles greater than 31 degree, it suddenly slides down. So due to the action of gravity. So but we just analyzed it for angles on which we saw the toppling motion, and on which we saw the specific motion, and then we found the extremum times.
And so, as for point, I'll pass the answer. So, why this velocity doesn't go to 0 or infinity? So that it don't go to infinity because of while beam goes down, its kinetic energy increase because of its potential energy decrease. So it transfers to kinetic one, but it doesn't increase to infinity because of there are because while motion beam hits the plane, so there's no longer collision, and there are lots of energy on it, and also ball hits the capsule while being inside it, and there's also wave energy losses, and so these energy losses and increase of energy, they become equal at some point, and after it, velocity remains constant because of losses are equal to increases.
Okay, thank you.
I have a question to both teams. As far as I understand from the slide, the plank was made of wood. No, is a wooden plank. Am I right? This is what is written. So
yes.
Yeah. Now, okay. Just give an estimation. What is your feeling if you change the material, the material of the plank? In the sense, of course, any material has a different elasticity, for example, so a different response to the movement. So what happens your what is the feeling you have if you change with the plank with different materials, how your analysis, your results could change. This is for the reporter and for the opponent.
Okay, so if we change the material, if the material is smoother, I guess that there would be faster motion, and if it is maybe for a smoother material, there would be very less amount of tumbles and more slipping or rolling, furthermore, to analyze this with our theory, we have incorporated the effects of friction in our theory. So the values of mu, they also change when the material of the plank changes. So we can also simulate this by varying the value of mu in our simulation, and we would get plots and results.
If I can just add, is not my question was not only concerning the friction, how the plank participates, the material of the plank participates to the movement of the capsule. This is basically. Do you think there is an effect not only in the friction side, also in the elasticity each time the capsule is jumping? Is it increasing the energy of the capsule or not? Depends on the elasticity or not? This was the question.
Well, the motion might change a bit, and the tumble might also change a bit, because there is also a change in the coefficient of, there can be a possible change in the coefficient of restitution as the capsule falls on the plank and then gets back up. So, and there can also be more slipping or less slipping depending on the material of the capsule.
Could I have a fast comment also from the Russia team?
Yes, of course. So
very quick.
Very quick.
I'll divide my answer into parts. First, I'll talk about the roles of friction. If the angle of inclination is small enough, in this case, changing material with the same elasticity parameter, not only friction coefficient, we won't change the dynamic of system at all, because we have non-slipping area. If we increase inclination angle and will work in the slipping area, in this case, increasing friction coefficient will surely decay the beam motion. And second, about elasticity, if we have surface like wood, in this case, capsule will stop at collision without jumping after collision. But if you take some more elastic surface, it can jump after collision, and so it will lose part of energy on this collision, and because of it, it will go down faster. I think I will answer your question.
Okay, thanks.